Hello everyone, good morning. Today I am going to discuss the very fundamentals of embedded systems, which form the background of many modern electronic products we use in our daily lives. In this lecture, actually designed to give you a clear and structured introduction to embedded systems, especially for those who are new to this field, including our undergraduate student, postgraduate students, or those who are really interested to work in this particular field. So they will get some little bit idea about the concept of embedded system by after completion of this video lecture. So in this session, I will begin by understanding what an embedded system is and how it differs from general purpose computing systems. So I will then explore the key characteristics that define embedded systems such as real-time operation, then reliability, efficiency, and application-specific design. This lecture will also introduce the basic components of embedded system, including processor, then memory, input-output interfaces, and software elements. Further, I will briefly discuss the common embedded system architectures and development platforms, highlighting how hardware and software work together to achieve specific functionality. Then important development challenges such as power constraint, then cost optimization, then performance requirement and reliability will also be addressed in this session. And finally, I will look at some real world applications of embedded system in areas such as in consumer electronics, then automotive systems, then medical devices, then industrial automation, and some latest technology which is called popularly it is known as smart technologies. So the main objective of this 1 hour lecture is to build a strong foundational understanding of embedded system, which will serve as a base for more advanced topics in future. Now I'm going to discuss about the definition of embedded system. What are embedded system? Why embedded system is nowadays is very much popular, that I will discuss. So the definition of embedded system is it is a specialized computer system developed to perform a specific or dedicated function, often often under real-time constraint. Unlike general purpose computer such as desktop, laptop, then laptops, so embedded system are designed for a particular application and optimized for efficiency, reliability, and cost. So these systems are usually integrated into a large product or device where they monitor, control, or manage operations. So embedded systems are not intended to be directly programmed by end user and operate with minimal user interaction. They are embedded within a device that they control working silently and efficiently in the background. Now coming to the slide number 3, here I am going to cover the key characteristics of embedded system. What are the different types of what are the characteristics are there for embedded system application? The first characteristic is dedicated function. Second characteristic is real-time operation. Third characteristic is resource constraint. Fourth one is reactive and real-time behavior. Fifth one is high reliability, and sixth one is tight hardware and software integration. That is the total six characteristic. There are other more features or other characteristics are there, but I'm going to discuss. I'm going to cover only this six important characteristics of embedded system. So the first one is dedicated function. So what do you mean by dedicated function? Generally in embedded systems are designed to perform a specific task or well-defined set of functions. Unlike general purpose computer, they are optimized for a particular application which improves the efficiency, performance and cost effectiveness. That means embedded system is task specific. In for any embedded product having maximum 4 to 5 application, not more than that. Like in general purpose computing system, we can see there are thousand or more than thousand number of application can handle by one general purpose computer, whereas embedded system is very task specific and very limited number of application can be performed with that particular device. Second one is real-time operation. So it is very important for any embedded product, that is many embedded system must respond to inputs or even within strict timing constraints. So timely and deterministic responses are essential in applications such as in automotive control, then medical equipment and industrial automation. So real-time operation is one of the key feature of embedded system. Next one is resource constraint. So embedded system typically operates with limited processing power, then memory, storage and energy. So efficient hardware selection and optimized software designs are required to meet the performance goal within these constraints. Next one is reactive and real time behavior. So this system continuously monitor external conditions through sensor and react immediately to changes or events. They operate in real time, providing predictable responses rather than batch processing. So this is another important characteristics of embedded system. Then next one is high reliability. So what is the meaning of high reliability? Actually, embedded systems are often used in critical applications and must function correctly for long periods without failure. They are designed to be stable, predictable and robust even in harsh operating environments. Then next one is tight hardware and software integration. So what is the meaning of tight hardware and software integration? Means the software in embedded system is very closely coupled with the hardware, and it controls such as sensor, then actuators and communication interfaces, enabling precise control and efficient operation. That is the that is actually known as the tight hardware and software integration. So next, in the next slide, I'm going to discuss about the examples of embedded systems. So there are so many areas in application in this particular embedded system product. So am highlighting here few areas, not all. So mostly most of the industry, automotive system industries are using embedded system. Then consumer electronics industry also using the embedded system. Then industrial automation, then medical devices, then aerospace system are using embedded system. So embedded system is now versatile. It is a versatile devices and it is useful everywhere, each and every sector. So the first domain is automotive systems. So automotive system in embedded systems are extremely used in modern automobiles to improve the performance, safety and comfort. So engine control unit like ECU actually manages fuel injection, ignition, timing and emission control. Then anti-lock braking system, that is called ABS, used embedded controller to prevent wheel locking and enhance vehicle stability. Infotainment, the system provides the navigation, entertainment, and connectivity features within the vehicles. So this is actually comes under automotive system. Next one is consumer electronics. In consumer electronics, embedded systems enable smart and automated operations of everyday devices. Then smartphones use multiple embedded systems for communication, then camera processing, power management, and user interaction. Uh, these are the consumer electronics. Then digital cameras rely on embedded processors for image capture and enhancement. Then appliances such as washing machine and micro oven, then air condition used to embedded controller to manage the timing, temperature and operational modes. Next application is industrial automation. So embedded system plays a vital role in industrial environments by automating processes and machineries. Mainly programmable logic controller, that is known as PLC controller, control production lines and industrial equipment. Then in robotic system uses the embedded controllers for precise monitoring and control, then sensing, then task execution, then these are the applications of in the robotics domain. Then in the process control industry, in process control system continuously monitor and regular industrial parameter to ensure efficiency and safety. Now next come into the another application, that is in the medical sector, medical device implementation. In healthcare, embedded systems are used in critical and life-saving equipment like pacemakers mainly monitor heart activities and deliver electrical pulses when it is required. Then insulin pumps control the accurate delivery of insulin for diabetic patient. Then medical imaging equipment such as MRI and CT scanner dependent on embedded system for control and data processing. Then next sector is application sector is aerospace system or aerospace industry. So in the aerospace sector relies on embedded system for reliable, precise operation. Then flight control system maintaining aircraft stability and control. Then navigation system assist in positioning and route planning. Then satellite system used embedded controller for communication, then data handling and orbital management. So these are the application area in embedded system. Now coming to the next slide, that is components of an embedded system. It is very important for any modern electronic applications. So what are the components are available in embedded system? So an embedded system is a combination of hardware and software designed to perform a specific function within a large system to achieve reliable, efficient and real-time operation. So an embedded system is built using several essential components. Each components play a distinct role in the overall functionality of the system. The major components are I'm going to explain one by one. So the first one is microcontroller or microprocessor. You can see in the at the left side, I have mentioned the microprocessor and microcontroller. So the microcontroller or microprocessor actually acts as the brain of the embedded system. It is responsible for execution program instruction processing data and controlling other components which is connected with that system. So based on this application requirement, designer may choose either microcontroller or microprocessor. So now I'm going to discuss very brief about the microcontroller, because within 1 hour I cannot complete the entire embedded system, but by after completion of this particular lecture, you will be able to understand the fundamental or basics of embedded system. So now I am going to discuss about the microcontroller. So what is microcontroller? So microcontroller is a single chip computer that integrates multiple components in one single chip, and it includes processor, core, the memory, RAM, ROM, flash, and input and output peripherals. Then microcontroller are widely used in embedded system because of their compact size. It is low cost and low power consumption. They are ideal for dedicated and real-time applications such as washing machine, the micro ovens, motor controller, and sensor-based systems. Since all essential components are integrated, microcontrollers simplify system design and reduce external hardware requirements. Next one is microprocessor. So a microprocessor consists primarily of a processor core without integrated memory or peripherals. Means a microprocessor is a you can say microprocessor is memory-less or input-output peripheral-less device or electronic chip, whereas microcontroller consists all these things: memory, then input-output, everything will be incorporated in a single chip. So in microprocessor, it is means in microprocessor we need to add memory and other peripherals externally. That is the difference between microprocessor and microcontroller. So in microprocessor, it requires external memory chip, I/O controller, and other peripheral devices to function. So another important point is microprocessor are typically used in high performance embedded system where complex processing is required, such as multimedia system, then embedded Linux platform, and networking devices. So such kind of area we can use microprocessor, and they offer greater flexibility and computing power, but increase system complexity, cost, and power consumption. Next, coming to the another important segment, that is called memory segment. So memory is a critical component of an embedded system as it stores both program instruction and data. So different types of memories are used depending on speed, volatility, and storage requirements. So memory selection directly affects the system performance and reliability and the cost. So first I'm going to discuss about the ROM. So what is ROM? ROM is a non-volatile memory used to store the firmware or permanent program code. So the content of ROM are actually retained even when power is turned off. That is the feature of ROM. ROM is a permanent memory storage element where you can store your program or any firmware or any firmware means any device driver, okay, driver programming you can store inside that particular ROM. And it typically stores both code and application software that does not change frequently, like in mobile phone. Whenever we are installing the software, that is actually one time we are installing one time. If any issues during runtime in the operating system, if any issues are coming, only on that time only we are formatting, like similar like our personal computer. We will not format multiple time of our operating system. So for such kind of software we need to store inside the ROM. So ROM basically used for permanent storage device in our embedded product. Then some variants of ROMs are available in the market, like PROM stands for programmable ROM, then EPROM, EPROM stands for electrically programmable ROM, and third one is electrically EPROM, which is known as electrically erasable programmable ROM, which allow limited programmability. So these are the different types of variants of ROM. Now next I'm going to discuss about the RAM. So what do you mean by RAM? RAM is a volatile memory used to store temporary data during system operations, and it holds variables, intermediate results, then stack and heap data, then mainly temporary data it is stored. And whenever the power supply is on, only on that time it will hold some information. When power supply is off, it will remove all the data. So that's why it is called volatile memory. So data in RAM is lost when, just now I told, when we will remove the power supply. And sufficient RAM is essential for smooth execution for program especially in real time and multitasking system. Means RAM basically used whenever we are performing any real time operation, for example face recognition or biometric identification in terms of retina identification, sorry, for retina detection, iris detection or fingerprint detection. For that we need sufficient amount of RAM, and it is useful for real time or multitasking system. Next one is flash memory. So flash memory is a non-volatile memory used for storing firmware and data, same like ROM. So it allows programming and updating of software without removing the chip. Then flash memory is widely used in modern embedded system for firmware upgrades and data login, and it combines the advantages of ROM persistence and reprogrammability. Then next one is input and output interface. So IO interface enables the embedded system to interact with external environment. Inputs basically allow the system to receive data from sensor, switches and user interfaces, and outputs allows the system to control actuator, display, motors and indicators. Then efficient IO handling is essential for real-time response and system control. So that is the feature of input and output interface. So by using input and output interface, we can connect with our embedded product in real world. Next one is analog to digital converter. So this under input output connection, analog to digital converter is coming. So ADC actually converts analog signal into digital signal or digital values that the processor can understand. So sensors such as temperature, pressure, then light and sound produces analog signal, and ADC sample these signals and convert them into digital form for processing. And another important feature of ADC is resolution and sampling. So resolution and sampling rate of ADC directly impact the system accuracy and performance. That is the characteristics of analog to digital converter. Now coming to the digital to analog converter, the same thing, but the operation will be vice versa. Like in analog signal to digital signal conversion by using ADC, but by using digital to analog converter, we can convert digital signal to analog signal. So what is the function? I will explain about the digital to analog signal converter. So DAC performs the reverse operation of ADC. Just now I told, they convert the digital data into analog signals such as voltage or current, and DAC are used in application like audio output, then motor control and signal generation. They enable embedded system to control analog device precisely. Then serial communication interfaces. So serial interfaces allows communication between the embedded system and external devices using fewer wires. So the first one is UART. UART stands for Universal Asynchronous Receiver and Transmitter, is used for simple serial communication. Then SPI. SPI stands for Serial Peripheral Interface, supports high speed communication with peripherals like sensors and memory devices. Then next one is coming I2C. So I2C stands for Inter-Integrated Circuit, which allows multiple devices to communicate using only two wires. That is the feature of I2C protocol, or I2C serial communication interface. So these interfaces are essential for data exchange, debugging, and system expansion. Next, coming to the parallel communication interface. So parallel communication interface use multiple data lines to transfer data simultaneously, like GPIO. GPIO stands for general purpose input output pins that are most common parallel interface. These GPIO pins are used to read switches, control LED, drive relays, and interface with digital devices. And they provide simple and fast control, but require more pins compared to serial communication. Then next one is peripherals. So peripherals are specialized hardware component integrated within or connected to the processor. They enhance the system functionality and reduce the software complexity. Some common peripheral includes like timer, counter, communication modules, and signal generators. So peripherals actually upload the repetitive or time critical task from the CPU. Number four, now coming to the timers and counters. So timers and counters are essential peripherals in embedded system. So timer actually generates the delays, schedule task, and manage time-based event, whereas counter counts the external events such as pulse or clock cycle. Okay, they are widely used in real-time system, then control application and performance measurement. Now coming to the another important components, that is PWM, that is known as pulse width modulation. So generator, pulse width modulation generator. So PWM generator produces a digital signal with varying duty cycle. So we can change the duty cycle based on our application. So PWM is used to control the motor speed, then LED brightness, and power regulation. So it allows efficient control of analog behavior using digital signals. So PWM is widely used in power electronics and automation system. Next coming to the communication module. So communication module enables the connectivity with networks and other devices. So example including Ethernet, Wi-Fi, Bluetooth, and CAN modules. So these modules actually support data exchange, remote monitoring, and IoT applications. So communication capability significantly expands the functionality of the embedded system. Now coming to the another component that is very much essential for any embedded product development, that is power supply. So the power supply provides the necessary electrical power to operate the embedded system. It converts external power sources into required voltage and current levels. So proper power design ensures the stability, efficiency, and protection of the components. So power management is especially critical in battery operated and low power embedded systems. So each component of embedded systems plays a very vital role in ensuring reliable, efficient, and application specific operations. A well designed embedded system carefully balances the processing capability, memory interfaces, peripherals, and power requirement to meet real-time constraint and functional goal. Now coming to the slide number 6. This is slide number 6. So here I am going to discuss about the common embedded system architecture. What are the common embedded system architecture is available in the market? So the embedded system architecture defines how hardware and software components are organized and interact with each other. The choice of this architecture actually depends on the application requirements such as performance, then real-time behavior, resource availability, then power consumption, and system complexity. So several architecture patterns are commonly used in embedded system, and each has its own advantages and limitation. So this architecture are explained below in a clear point by point manner. So the first one is uh, bare metal programming. So you can see in this slide I have mentioned at the top bare metal programming. So what do you mean by bare metal programming? bare metal programming is the simplest and most fundamental embedded system architecture. So in this approach, the application code runs directly onto the hardware without the support of operating system, and the programmer has full control over the processor, the memory and peripherals, which allows for highly optimized and deterministic system behavior. This architecture offers maximum performance and minimum overhead, making it suitable for low cost resource constrained systems. Then these bare metal system are commonly used in simple applications such as LED controller, basic sensor nodes, then small consumer appliances. However, development can be challenging because the programmer must manually handle task scheduling, then timing and hardware resource management. So next, second architecture is called real-time operating system architecture. So a real-time operating system is designed specifically for application that requires predictable and timely response. So an RTOS provides services such as task scheduling, inter-task communication, then memory management and synchronization mechanisms. So it enables developers to divide the applications into multiple tasks that run concurrently based on priority. So RTOS based system ensures the deterministic behaviors, which is essential for real-time applications like automotive control, medical devices and industrial automation. By managing low-level details, an RTOS simplifies application development and improves the system scalability. However, RTOS-based systems require more memory and processing resources compared with bare metal design. So in the next slide, I'm going to discuss about the another two architecture, that is embedded Linux. I think previous slide I missed. Okay, so in the third one is actually example of a real-time operating system. Several real-time operating system platforms are widely used in embedded system development. Mainly, FreeRTOS is popular due to its lightweight nature and open source availability. Then Zephyr provides a scalable and secure RTOS framework suitable for IoT applications. Then RT-Thread offers modularity and real-time performance for a wide range of embedded devices. Then VxWorks is a commercial RTOS commonly used in aerospace, defense and safety critical system. Then next one is embedded Linux. This is another architecture, embedded system architecture. So embedded Linux is a Linux based operating system tailored for embedded applications. It provides a rich set of features including multitasking, networking, file systems and device drivers. Okay, so embedded Linux is highly flexible and support complex applications such as multimedia processing, gateway and smart devices, and developers get benefit from a vast ecosystem of open source tools and libraries. However, embedded Linux requires significantly more memory storage and processing power than bare metal or RTOS based system. So it is best suited for high-end embedded system where resources are not severely constrained. Now coming to the system on next architecture, that is system on architecture. So system on chip architecture. So system on chip integrates multiple system components into a single chip. It typically includes the processor, memory controller, then communication interfaces and peripherals. So SoC actually reduces the system size, power consumption and overall cost. They are widely used in complex embedded systems such as smartphones, automotive platform and IoT gateways. SoC support advanced architecture like RTOS and embedded Linux, enabling powerful and compact system design. So each embedded system architecture offers unique benefits and trade-offs. By selecting the appropriate architecture is crucial for achieving optimal performance and reliability and efficiency in embedded system design. Coming to the slide number, this is my current slide, slide number 8. Here I am going to discuss the embedded system development process. So what are the steps we need to follow during embedded system product development? So the first one is called a requirement analysis. So this is the first and most critical stage of embedded system development. So the system functionality, then performance expectation and operation constraints are clearly defined. So requirement includes timing constraint, then power consumption, then cost limits, then environmental condition, then reliability, then safety standard. A detailed and accurate requirement analysis helps to avoid design errors and reduce network in later stage. Now second stage is system design. So in this stage the overall hardware and software architecture of the embedded system is planned. So designers select the appropriate processor, microcontroller or microprocessor, then memory, communication interfaces, and operating system. So operating system like bare metal, RTOS, or embedded Linux. Okay, so this system is divided into modules and data flow interfaces and communication protocol are defined to ensure efficient integration. So next, third one is hardware development. So what do you mean by hardware development? Hardware development involves designing and building the physical platform of the embedded system. This includes component selection, schematic design, then printed circuit board layout design and power supply design. So hardware prototypes are created and tested to verify correct electrical operations, signal integrity and compliances with design specification. Next one is software development. So the fourth one is software development. So software development focuses on writing and testing the code that controls the entire embedded system. So this includes developing device driver, middleware, then application software. So the code is actually optimized for performance, memory usage, and real-time response. So unit testing and debugging are performed to ensure reliable and software behavior. So this is comes under software development life cycle. So this is one part of this embedded system product development life cycle. Now coming to the next one is called integration and testing. So in this phase, actually what we will do, hardware and software are combined into a complete system, and a comprehensive testing is carried out to verify the functionality and timing, performance and reliability under real operating condition. So integration testing helps identify issues related to hardware and software interaction and system stability, whether systems are working or functioning properly or not. So that is called integration and testing. Integration means integrating to the hardware and software, and after that to verify whether software based on these software instruction, whether hardware is responding properly or not. Okay, so that is called integration and testing. Now next one is deployment. So deployment actually involves the installing the embedded system in its target environment. So in the final firmware is actually programmed, and the system parameters are configured, and compatibility with the external system is verified. So the system is actually prepared for real world operation. Now last one is the maintenance. So what is maintenance? Maintenance actually ensures the long-term system performance and reliability. So this stage includes monitoring system behavior, then fixing bugs, providing firmware updates, and implementing enhancement where required. And proper maintenance and extends the lifespan of the embedded system and supports evolving user need. Okay, so definitely for any after like our mobile phone, when it is came from the manufacturing unit and when we purchase that particular mobile phone, okay, first time we will use, after 1 year if something happened, then what we will do, we will send into maintenance department. So maintenance department will rectify whether this in the system, whether any errors or any debugs are available or not. If it is there, then they will they will maintain that, they will remove that. So this is actually detailed discussion about the embedded system development process. Now coming to the development tool, what are the embedded product development tools are available in the market? The main tool is integrated development environment, that is called IDE. So integrated development environment provides a complete platform for embedded system software development. They combine code editing, compiling, building and debugging tools in a single interface. So IDE improves the productivity by offering features such as syntax highlighting, and then project management, and real-time error detection. So most popular IDE used in embedded development including Keil software, Kill Vision software, then IAR embedded workbench, then Eclipse, which supports a wide range of microcontroller and development board. Next one is compiler. So compilers are essential tools that translate high level source code to which is written in language like C and C++ into machine code that embedded processor can execute. So an efficient compiler ensure optimized code generation, reduce memory usage and improve the system performance, which are critical in a resource constant embedded system. Next one is debugger. Debugger helps developer to identify and fix software errors by allowing step-by-step execution of code. They enable inspection of variables, registers, and memory location while the program is running. So debugger are actually crucial for understanding program flow and resolving the logical and timing related issues. That is the purpose function of compiler. Then next one is emulator and simulator. So emulator and simulator actually replicate the behavior of the embedded system on a host computer. They allow developers to test and analyze system behavior without physical hardware, making early stage development faster and safer. Now this is called emulator and simulator. There is another important embedded development tools, that is called logic analyzer and oscilloscope. So logic analyzer captures and analyzes digital signals, while oscilloscope measure analog signals such as voltage and timing. So these tools are vital for debugging hardware interfaces and signal integrity issues. Then coming to the next slide, that is slide number 10, that is challenges in embedded system development. So what are the challenges we are facing now? Our engineers are facing daily for embedded product development. So the first one is resource constraint. So the first point is resource constraint. So embedded system actually typically operate with limited memory, then processing power, storage, and energy. So designer must optimize both hardware and software to function efficiently within this constraint. So carefully memory management, efficient coding practice, and optimized algorithms are essential to achieve acceptable performance without exceeding the available resources. The next one is real-time requirements. So many embedded systems must respond to external event within strict time deadline. So missing this deadline can cause system malfunctioning or safety risks, especially in applications such as automatic control, then medical devices, then industrial automation. So to ensuring this deterministic execution and predictable response, time is major challenges. Okay, so this is very important challenges. And next one is hardware software integration. So embedded system rely on close interaction between hardware components and software control logic, ensuring seamless communication between processor, peripheral sensors, and actuators requires a thorough understanding of hardware behavior and timing. So poor integration can be lead to unexpected system behavior and reliability issues. Okay, now next point is reliability and safety issues. So embedded systems are often deployed in critical and long-term applications where failure is unacceptable. So they must operate reliably over extended period or under harsh environmental conditions such as high temperature, then vibration and electrical noise. So implementing fault tolerance, error detection, and fail-safe mechanism is essential to ensure safe operation. Next one is security. So with the growing of connected and IoT based embedded systems, security has become a major concern. Embedded devices are vulnerable to unauthorized access. So data for data theft and cyber attacks. So to protecting such firmware or communication interfaces and stored data through encryption, authentication, and secure boot mechanism is one of the significant challenges. Okay, so security is another important concern. Now coming to the debugging complexity. So debugging complexity, actually debugging in embedded system is difficult due to limited system visibility, real-time execution, and restricted access to internal states. So traditional debugging techniques are often insufficient, requiring specialized tools such as in-circuit debugger, logic analyzer, and oscilloscopes to identify and resolve the issues. So next one is power management. So power efficiency is a critical challenge, particularly for battery operated and portable embedded system, like where rechargeable battery is needed for long duration of time. This is one of the biggest challenges. So designer must balance the performance with energy consumption by using low power hardware, then efficient software design and power saving technique to extend the battery life and ensure sustainable operation, like our mobile phone. You can see if we are continuously, if we are using our mobile phone for net surfing or other phone calling or other thing, automatically what will happen, power bill goes down. So designer actually thinking about such kind of product, so that one particular device, what device we are using now in our daily life, like mobile phone. So how to make that mobile phone, user can access any data, anything in the mobile phone, but it must consume very less amount of power. That is the main objective or main intention for any embedded product development engineer in terms of power management concern. Now coming to the next, already I have explained few points about the real world application. So still I'm going to cover few things, like in which particular area it is very much useful, like automotive applications, then consumer electronics. Okay, in automotive industry like engine control, then braking systems, then infotainment, then driver assistant. These are the real-time example, like consumer electronics, like smartphone, wearable devices, home appliances, then gaming consoles. These are the consumer electronics. And another consumer electronics is process robotics, then process control. Okay, so these are the area of application, real world application. Then some industrial automations also there. Medical devices are there. In healthcare, embedded systems are used in critical applications that require high accuracy and reliability. So patient monitoring system continuously track the vital signs such as heart rate, blood pressure, and oxygen levels. So it is very important. So different devices we're using, like MRI, CT scan, ultrasound machine, depends on embedded system for data acquisition and image processing. So this is the application. Now in the aerospace area also, there is so many areas where we can explore, like satellite communication, signal processing. Okay, so these are the for navigation purpose, then flight control system. Okay, aircraft management system. We are using embedded product in real time, and these are the real world application. Then now this is one of the trending area that is known as internet of things. So embedded system form the foundation of IoT applications. So smart home use embedded devices for lightning control, security system, and energy management. Then smart cities deploy the embedded system for traffic management, waste monitoring, and public safety. Then connected devices enable remote monitoring, collection, and intelligent decision making across the various industries. Okay, So these are the real world applications. Now coming to the last slide. This is my last slide. Now I am going to conclude my session. So in conclusion, I can say that the embedded system form the backbone of modern technology and are essential to the functioning of numerous devices and applications across industries such as automotive, then healthcare, then consumer electronics, industrial automation, aerospace, and IoT. So their ability to perform dedicated tasks efficiently, reliably, and often in real time makes them indispensable in today's digital world. So a clear understanding of embedded system fundamentals includes their characteristics, core components, system architecture, then development process is crucial for designing effective and reliable solutions. Then knowledge of common challenges such as resource limitation, real-time constraint, power management, security, and system reliability further equips engineers to develop robust embedded applications. As the technology advancement is continuing, so embedded systems are becoming more intelligent and interconnected and capable. So some emerging trends such as artificial intelligence, the smart sensor, then wireless connectivity are significantly expanding their scope and impact. So in conclusion, embedded system will continue to play a vital role in driving innovation and shaping the future of modern technology, making their study and development increasingly in our daily life. So thank you for today's discussion.